I did grade the quiz sometime yesterday, I think. So you should be able to sign into Gradescope and see how you did. I noticed that most of you checked it out, so you can see what score you got, like overall on the quiz, but you can also look question by question, which you should look question by question, see how many points you got on each one, so that you can keep track of it in your list. Remember that we have a regular homework assignment due tomorrow, and then on Friday we will again have a quiz, which will include questions on the homework topics, of which there are 3. Plus, you can do one old question from the first quiz if you want to, right? I hope, I've been thinking about exactly how, practically speaking, I'm going to manage this. I decided to make, this is like a little order form that I'm going to pass around. Check off which one you want to do from the old topics. So your name appears down here, and these are all the topics. Now you should only check one of the first 4 topics, or if you don't want to do an old one because you've got them all right, then just say, I don't want to do any of the old ones. That makes sense, everybody? I hope so. If you didn't quite get a chance to look at your grades, and so if you're not sure yet, that's fine too. I will bring this tomorrow also, but maybe check one off and pass it around. All right, let's get on with it then. I think we can. We are going to move to a new section today, and this is slightly strange, the way that our book handles this topic, but I want to talk about the natural logarithm. The natural logarithm. Logarithms are super important in math, I guess, and science in general. The natural logarithm is something that I hope that you've all heard of before, although the way in which we are going to discuss it is a little weird. The natural logarithm. And in our book, I'm not making up this weird approach. This is the approach that is taken in our book. Our book does it weird. And our book actually, I don't know if you are aware, this book by Stewart is kind of a legendary calculus textbook. And it's strange for a legendary book like this to handle a topic in a weird way. And so actually, for this reason, the book has like 2 parallel universes, 2 different versions of this whole chapter in the book. So we are going to talk about section in the book. You'll see this. I mean, you don't care unless you're looking at the homework problems probably, but this is section 6.2 star. There is also section 6.2 without the star, but we're not doing that. We're doing the one with the star. Those are 2 different treatments of the logarithm, and we're going to do the one with the star. That's the weird way. All right. The traditional way, and I assume this is the way that you've all experienced logarithms in high school, is first you talk about exponents, and then you say the logarithm is a way of doing that sort of backwards, right? So logarithms, I will give you, this is the usual presentation, is that logarithms are inverse to exponents. What I mean by that is something like every kid knows that, say, 2 to the power 3 equals 8, which means log base 2 of 3 equals 8. And I hope you're familiar with this kind of presentation. These 2 little equations are really saying the same thing. They're just saying it in a rearranged form. This is sometimes called the exponential form, and this is called the logarithmic form. But these 2 statements are really the same thing. They mean the same thing, it's just written differently. So it's kind of like if I said 1 plus 2 equals 3. Another way you could say that is 3 minus 1 equals 2, which is the same basic fact, although it's rearranged somehow. All right. And if you ever find yourself trying to explain what logarithms are, like to an ordinary person, this is probably how you should explain it. Although if they've never heard of this before, it's a little confusing. Anyway, that's the usual presentation. You talk about exponents first and then logarithms. But in our book, we discuss logarithms first, then exponents. All right. The reason to do it this way, this is a little strange, but the reason to do it this way is basically because I don't know exactly why Stewart decided to write his book this way, but I think it's because since the number e is weird, right? Like the natural logarithm in particular is kind of the nicest logarithm in terms of its mathematical properties, and the natural logarithm is the one which is inverse to powers of e to the x. The inverse of that is the natural logarithm. We are going to discuss this kind of the other way around, logarithms first and then exponents, because the number e is weird. Does anyone actually know the definition of the number e? E is a special number, of course.
2.7.
Yeah, 2.718.
Yeah, okay, so I don't mean what it is as a number, like what the digits are. I mean actually what it's supposed to mean. Like, for example, if you ask me what's the definition of pi, you can say the digits are 3.14, whatever, but that's not what I mean by what is it supposed to mean. Pi is supposed to mean the ratio of the circumference and the diameter of a circle, right? So what is e supposed to mean? Or does anybody actually remember? Do you remember?
Is it like the area under a curve and like 1 e or something? It's really neat. I don't know.
This is somehow related to something, but it's not what I was gonna say. That's not, in my experience, that's not typically how people say the number e is defined. I think the usual definition of e is this, which nobody should like this, but this is the typical definition if you look up what is the number e, what is it really, where does it come from? It's that. Very strange limit where if you try to, like if you show this to a high school calculus student and ask them to find the limit, they might try, I can just plug in 0 here. But then you have 1 over 0, which I don't really like, and you also have an exponent of 0, which I also don't really like. It's not clear what this limit is. It turns out this limit is, that's what e is. E is this special limit over here. But this limit, if you are trying to be kind of rigorous with everything, I would say it's not clear this even exists, right? And the most important property of e, at least as far as calculus is concerned, is that the derivative of e to the x equals e to the x. But that fact is definitely not obvious at all if this is the definition of what e is. So it's not clear this even exists, and not clear why e to the x is special in terms of calculus, right? Probably when you learned all of these facts, at some point your teacher said something like, you're just gonna have to take my word for it. Or maybe to find this limit, they said, you can find this limit by plugging in numbers on your calculator that are close to 0 for x, and you end up getting the digits of e. But this is not a very mathematically rigorous approach to the subject. You should not depend on some kid plugging numbers into their calculator to make sense of this definition. All right, so it turns out things from an abstract point of view, it's all easier to define ln of x first, and then derive stuff about e to the x. All right. So we're going to talk about the natural logarithm today, and then the inverse of that, we are going to say the inverse of the natural logarithm is e to the x. And that will be, for us, that's the definition of e to the x. It's the inverse of the natural logarithm. All right? I don't know if this is confusing at all, but this is how we're going to do it for the sake of being more rigorous about everything. Okay? So the natural question that should come to mind is how would you ever define the natural log first without ever talking about exponents or e to the x or anything like that? And this is actually related to something that she said. You can define all of these things in sort of a roundabout way by using area under the curve. So I think probably you all know, hopefully, you know the integral. Anybody know what's the antiderivative of ln x? Yeah?
Is it just 1 over x?
It is 1 over x, yeah. Plus c, of course. We can use this as a definition of the natural log of x. So to be specific, I'm going to say it like this. Here's what we are going to take as the definition. We define, this is not true. It's backwards.
Yeah.
Sorry about that. That's why you can use it as a definition, actually. It's this. That was a trick question when I asked, do you know the integral of natural log of x? Actually, there is a formula for that, but it's weird. It's not a nice looking thing. I misled you. The integral of 1 over x is the natural log of x. Did you ever get the paper? No. Still working on it.
Can you go for just like half a second? I just get the last part.
It's easier to define the natural log first and then derive stuff about e to the x. So this formula here with the integral sign, basically we're going to use that as the definition. That's what the natural log is. It is the integral of 1 over x. Did everybody get this? I think everybody got it. Anybody else need to tell me which one you want? What you really, really want? All right. So we define in this way the natural log of x equals. Now there is the small matter of the plus c. So it would be tempting to just forget about the plus c, and then that's a definition of the natural log. It equals the thing on the left-hand side. But that's, it's not okay to forget about the plus c exactly. So this is going to be a slightly weird-looking thing, but it is defined like this. The integral from 1 to x of 1 over t dt. This is weird, but you can draw a picture of what that is. It is a specific area under a curve, and in particular, it is this curve, 1 over t, all right? Now, I will just say this only makes sense if x is greater than 0, and you'll see why. What this means is the area under the curve of 1 over t, which of course looks like that, at least on this side of the xy plane. And we are taking the area starting at 1 and going up to x. So this area right here. This is the natural log of x. It's defined to be that area. So from this point of view, if you ask me, for example, what's the natural log of 2? I say it's whatever that area is from 1 up to 2. That's what the natural log of 2 is. This is different from the typical high school student's answer would be something like the natural log of 2 is whatever number you need to do e to some power equals 2. This is also a correct answer, but from our point of view, this is how we are going to define what the natural log of a specific number is. So, for example, ln of 2 equals, if you plug this into your calculator, something like 0.693, whatever, it represents specifically the area under this curve from 1 to 2. It's this area here, all right? And that number, if you wanted to calculate that number, if you really wanted to calculate that number, you could do it using something like Simpson's rule, if you've heard of that, or you could estimate the area under the curve by one of the other methods for adding up rectangles, Riemann sums, that kind of thing. So this actually, using this as a definition, you could, in theory, calculate what the natural log of 2 is by hand. You could approximate it at least. Whereas if you're not using this definition, actually it's quite difficult to calculate by hand. Anybody actually know how to do that? If I ask you, like, what's the natural log of 11? I'll give you a few minutes, work it out on paper. Can you do that? The answer is no, not really. There are some methods to do that, but it's not at all obvious how you would even start. At least this approach gives you some way that you could, in theory, work that out by hand, at least some kind of approximation. All right, anyway, this is how we define this. I said this only makes sense if the x is greater than 0. That's because here is where x goes. Now, you could put the x on the other side of the 1, and that would still make sense. You'd be doing the integral from 1 back down to x. But if you actually put the x way over here, that does not make sense anymore, because you will be trying to do the area from 1 all the way over here, which will go through this vertical asymptote, and that's not allowed. At least it's not something that you should do casually. So I will say this only makes sense if x is greater than 0, and maybe I'll put another parenthetical. If x is between 0 and 1, that means this area actually occurs kind of on the left, and when you do the integral from 1 down to there, it's going to be counted as a negative area when you do this integral. So if x is between 0 and 1, then the area counts negative, because you're still doing the integral from 1 to x. And if x is less than 1, then that's sort of a backwards integral. The area counts as negative. So the natural log of x is negative. And this is another basic fact about the natural log. If you have a number between 0 and 1, like the natural log, any log actually, of a fraction will be a negative answer. And it's because of this. It's because when you use x to be a fraction, it ends up to the left of the place where you're starting the integral. So the integral goes backwards, which makes the answer negative. All right. This is our somewhat weird setup, but I'm going to try to discuss all of the ordinary properties of the natural log function using this as the definition, this weird sort of area. All right, so this is our goal for the rest of today, probably. Can we derive all our favorite facts about the log? Using this definition, I will write it again. ln x equals the integral 1 to x, 1 over t dt, right? This is our goal for the rest of today. All right. Let's talk about my first favorite fun fact. Fun fact about the log. Number 1 is, anybody remember this? The natural log of 1 is 0. Yes, the natural log of 1 is 0. Now, if you ask the typical high school student, why is the natural log of 1 0? The typical answer is it's because e to the power 0 equals 1. And therefore, thinking it the other way around, the natural log of 1 equals 0. But this is not how I want to talk about it. Can you get the same result by thinking of it in terms of this definition here? Any thoughts about that? Actually, it follows immediately from this definition also. What do you think?
If you have 1 and 1 as like your a and b, then it's just going to equal that number.
Yeah, right. We can just straight up plug in x equals 1 to this definition, all right? This is actually, in my experience, something that high school students hate about the natural log is you cannot just plug in some x to some formula and get the natural log. Like if I ask you what's the natural log of 8, you can't just plug in x equals 8 and figure it out because there is no formula. Here, there is a real formula. It's this. So plug it in. Plug in x equals 1 to the definition. What we get, integral 1 to 1. This is natural log of 1. 1 over t dt. And this is a basic fact about the integral. If you are doing the integral from something up to the same point, then this is 0. This is 0 area. From 1 up to 1, there's no area there. So this is 0. That's because there is no area. If you have an integral from a to b and a and b are equal, then the answer is always 0. All right? Great. This is our first fun fact. The natural log of 1 equals 0. I like that. Any thoughts about that one? There's some kind of knocking in this room every so often. Okay, another fun fact about, actually, I meant to say this other one before that. This is even funner in terms of calculus. The derivative of the natural log. Do you know the derivative of the natural log? This is what you thought I was asking before. Anybody remember this? Yeah?
1 over x.
It's 1 over x, yeah. You're all worried because I said it backwards the other time. The derivative of the natural log is 1 over x. Can we demonstrate that using this definition? Yes, actually this is easy. This is another fact. If you actually want to prove this rigorously, using the exponential first approach is not at all easy to do. But this is fairly easy. How do we do it? We would just plug into the definition, use the definition. It will say derivative of natural log x. Remember the definition is integral 1 to x, 1 over t dt. Can you do anything with that? This is very weird. Derivative of an integral of something or other? Yeah?
We just cancel.
Yeah, when you have the derivative of an integral, the derivative and the integral sign kind of cancel. The whole integral sort of evaporates, and all you get is this function on the inside. This is what we call the fundamental theorem of calculus, the first version. We talked about this on the very first day of class. The answer is just 1 over x, because the derivative cancels the integration, and all you end up with is whatever this function is, but using the x variable rather than the t. All right? This is by the fundamental theorem of calculus, part 1. All right? Excellent. So I'll put this in another box. This is another fun fact about the derivative of the logarithm. It says, all right, what else? I got 2 more main fun facts, and then we can talk about something slightly different. The next sort of important fact about the logarithm that people learn is about this. Log of AB. Anyone remember what you can do with this? There's something or other.
Natural log of A plus natural log of B.
Yeah, right. This is the natural log of A plus the natural log of B. All right, can we demonstrate that? Again, you can also demonstrate this in terms of the using the definitions or whatever. Actually, this one I'm not going to use the integral sign. I'm going to consider the derivatives of this. So I would like to say, so I'm going to use x instead of b. This makes it a little easier to, you could call the variable whatever you like instead of b. So what I want to show that natural log of ax equals natural log of a plus natural log of x. All right? And the way we're going to do this is by taking the derivative on both sides. So let's consider derivatives. Our goal is really to show that both of these things are straight up equal. What I'm going to show first is, first of all, demonstrate that they have the same derivative. This will mean that those 2 functions maybe are not equal, but they're different only by a constant, and then we can do some other business. So let's consider the derivatives. The derivative of the left side would be the derivative of ln ax, right? Where we're considering a to be a constant and x is the variable. Here you have to use the chain rule, the derivative of the natural log of ax. Can anybody say what this is going to be if you use the chain rule? Of course, you should use this fact, which you can see at the top there. Derivative of ln x is 1 over x. How do we do it for this ln ax?
It's just 1 over x.
1 over x? What about the a?
Because when you do product rule for the chain rule, doesn't it cancel out because it's a over 1 over ax?
Yes, yeah, so I just want to write out the details of that. I'm considering a to be a constant. So this, I get, first of all, 1 over ax, because this is this rule here, derivative of ln x is 1 over x. So whatever it is, you just go 1 over whatever. And then you have to do the chain rule. You go times the derivative of the inside. And since a is a constant, the derivative of a times x is a. So this is times a. That right there is the chain rule. That extra times a there is multiplying by the derivative of the inside. But anyway, the a's cancel, like he said, and I end up with just 1 over x. All right. So the derivative of log ax is 1 over x. And what about the right-hand side? Remember, I was looking at the two sides and taking the derivative of each one. So let's also take the derivative of the right side. ln a plus ln x. Now, if I'm considering if I'm considering a to be a constant, that means that ln a is also a constant, and so that part will become 0 when I take the derivative, and all that I get is the derivative of ln x, which is, maybe I'll just write 0 plus 1 over x, right? ln a becomes 0 because there's no x there. ln x becomes 1 over x because that's what the derivative of ln x is, and so this is 1 over x. All right. Now, what you see so far is this derivative is 1 over x, and also this derivative is 1 over x. Okay, so the natural log of ax and ln a plus ln x have the same derivative. And so this means that they differ by a constant. If two functions have the same derivative, then they are different by a constant. So that means, so I could say ln of ax is equal to the other one, ln a plus ln x, plus some constant. This is for some constant c, right? If two functions have the same derivative, then they are differing by a constant. And now finally, what is the c? Can we, what I would like is for the c to be 0. What is the c? We can find the c by plugging in a single value. Find c by plugging, and I choose to plug in x equals 1. This whole thing then, if I plug in x equals 1, it says ln of a times 1 equals ln of a plus ln of 1 plus c. And can we simplify anything in there? I want to solve for c. What do you say? Yeah?
ln of 1 is 0.
ln of 1 is 0. That's something that we already said. And then what about the rest of it? I have ln a here and ln a plus 1. I think those can cancel, right? They're the same. A times 1 is a, right? So these guys actually, on either side, you can just subtract them away. And the fact that ln 1 equals 0, that means this whole thing says 0 equals c, right? So that means what I wrote before, ln of ax equals ln of a plus ln of x. Right? It used to say this plus c, but then we just determined that the c is actually 0. So this is everybody's favorite fun fact about multiplying the log of a product is the sum of the two logs. All right? Anybody got thoughts about that? This is how we come up with basic fun facts about the logarithm. How we doing? We're doing fine. All right. I got one more of these fun facts, and then we will be done with this. I don't know if you all are interested in seeing how where all of these basic rules come from. I know some people are not into the proofs, but it's important. And I, as a mathematician, am most definitely into the proofs. One other property, and that is, anybody remember this one? The log of a over b. What is it when you have a quotient inside of a log? Anyone remember? Yeah?
Subtraction.
Yeah, it turns into subtraction. So this becomes natural log of a minus natural log of b. All right? And this is related to, I will write this as a, anyone know what that is? Natural log of 1 over b? Yeah?
0.
It's not 0. It has to do with b somehow. Yeah?
Just negative ln b.
Yeah, it's negative ln b. Let's try and demonstrate the first one. Well, I want to do them both. The second one is a little easier. Can we do the second one first? So maybe I'll call this A and, is it confusing to label them as A and B? I think so. I'll call this number 1 and number 2. All right, let's do number 2. Where does that come from? Here's a cute little trick. Consider b over b, of course this equals 1, right? And so if I do ln of b over b, this of course is equal to ln of 1, which is 0, all right? But also, I can write the b over b, this is just a cute little trick, as ln of b times 1 over b, right? B over b is the same as b times 1 over b. And then by the rule that we talked about before, the multiplication rule, you can split that up into two parts. So this equals ln b plus ln 1 over b. All right? And if you read all of this together, so this thing equals 0, but this thing also equals that. That means, so ln b plus ln 1 over b equals 0. And then if we subtract ln b to the other side, so ln 1 over b equals minus ln b, like so. All right, and that's that second one there. ln 1 over b equals minus ln b. This is a thing that people like to write at the end of a proof. Sometimes you see people write QED. That's a Latin phrase, quod erat demonstratum, which means something like, I just done showed it. It means like, it has been demonstrated, or something like that. People write at the end of a proof. I have an old real analysis textbook from like 1910 or something. At the end of a proof, it says this, shewn, which I kind of like. So sometimes I write shewn at the end of a proof, and I chuckle to myself. All right, I did that one of these recordings, that I put them on YouTube. Sometimes just like random people watch them. Somebody said, actually, you should not say shewn. That word, it was written shewn, but they never pronounced it shewn. They pronounced it as shown. It's like the modern word so was never pronounced sew. It's just they spelled it that way. So I get a thumb down on that comment. I'm going to say shewn because it sounds silly to me. It's true, I guess. If this person is to be believed, nobody ever actually said shewn until me. All right, that was the second one. Can we just go, the first one now becomes easy. Number 1, if you're using number 2, how do you get number 1? It's a similar trick. So if I want to do ln of a over b, I write this as ln a ln of a times 1 over b, right? Split apart that fraction like so. And then you can use the product, the log of a product. So split up ln of a plus ln of 1 over b. And then by this one that we just said, up here, ln of 1 over b equals negative ln b. So this, therefore, equals ln a minus ln b. All right? So that's just a cute trick using the other rule. All right? All of these rules, though, what I want to emphasize, again, all of these rules are derived for the natural log without any reference to exponents or anything like that. All right, so you could, in theory, you could teach kids about logarithms like this. A log is just the area under the curve of 1 over x, 1 over t, whatever. All right? I actually don't suggest that you do teach kids logarithms in this way, but we are sophisticated adults here in a 4-credit calculus 2 class, so we can handle it. One last rule that I don't want to do the proof of, just because I think we've done enough proofs at this point, but one more cute rule is this: the natural log of something to a power. The natural log of a to some power r. Anybody remember this one? This one is actually quite useful.
It's just all.
It is not just r. I mean, the a doesn't go away entirely here. If it was ln of e to the r, then it would be just r. Yeah?
Is it ln a times r?
Yes, and I'm going to write it this way: r times ln a. Yeah. The number, which is the exponent inside of the log, can come down to the front as a coefficient. And this sometimes people are a little confused about this. This is not a derivative rule. This I'm not talking about the derivative at all. This just this thing straight up equals that. They are the same thing. When you have a power inside of a logarithm, it is the same as that power coming down as a coefficient. From a certain point of view, this is the whole point of the logarithm in terms of doing algebra using logarithms. This one is actually super important. This is how you are able to solve for variables which exist inside the exponents of things. But anyway, that's I'll leave it at that. I don't think we need to do the proof of that one just because we've done enough. But it can be done along similar lines as the ones that we've just done. All right. All these rules together, I hope you're familiar with these rules all together, but you can use them to simplify logs in nice ways. So we can use all these to rewrite equations involving logarithms. I keep on saying logs. I mean, technically I'm only talking about the natural log here, but actually you probably already know all of the same rules are also true of the other logarithms, which we will eventually talk about the other logarithms. Anyway, for example, the natural log of the square root of x times sine of x. This can be rewritten to look different. And in various, I mean, in some settings, maybe that already looks good to you, but can anyone suggest how we could rewrite this to re-simplify it somehow or rearrange it? First, I would say the wrong answer would be, can I just put the log inside of the square root? Is that allowed? No, it's not. But you can do something. I mean, not that, but yeah.
You could take the square root and make it 1/2.
Yeah, make the square root into a 1/2 power, and then you can use that rule that you see at the top there. So this would be x sine x to the power 1/2. And then, using the rule that you see at the top, the 1/2 can move down in front as a coefficient. So this is the same as 1/2 the natural log of x sine x. Can we do any more? Yeah?
You can use like the multiplication rule.
Yeah.
Make two separate logarithms.
Yeah, this is the log of something times something, and so we can split that up into a sum. So it becomes 1/2. We have to leave the 1/2 out there, but it becomes ln x plus ln of sine x, right? Now I'll leave it to you to decide, is there actually any point to rewriting it in this way? I don't know. I mean, in certain situations, it is good to be able to move from one format to the other, although this is just a made-up example. So, all right, great. Let's continue chatting about the natural log. Can we talk about, I just want to kind of give a brief tour of all your favorite facts about the natural log. How about the graph of ln of x? I hope everybody, if you've forgotten what the graph looks like, that's fine, because we're about to talk about it. I hope everybody has a vague idea of what the graph of the natural log looks like. Maybe I'll go below the bar here, just because my thing doesn't always like it. I'll refresh our memory. This is the definition. ln x is the integral 1 to x, 1 over t dt, right? What does the graph look like? So we've already discussed, we know this is really the only specific value that we know. The natural log of 1 is 0, so okay. That means if I were to draw this graph, actually we know a little bit more than that, and the domain is, I would write it as the integral from 0, the interval, the open interval from 0 to infinity, right? You don't plug negative numbers into the natural log. Actually, you can, and if you allow imaginary numbers, you get imaginary numbers, but we're not into that at this point. We know the natural log of 1 is 0, and its domain is 0 to infinity. So if I'm going to plot this, it goes through this point, right? The graph of the natural log, it goes through that point. And we also said that this integral, or this this function, in this range, it's negative, right? The log of a number between 0 and 1 gives you a negative answer. And if you think about, remember the definition here of this definition refers to this specific curve and then looking at the area under the curve, like from 1 to x, right? So I would say when x is bigger than 1, that area is positive, right? It's 0 here, and then it becomes positive. And as I go to the right, does it stay positive or does it go back negative at some point?
Positive.
Stays positive. Yeah, why do you say that? I don't know who said that.
The graph just goes up.
You mean because you already know what the graph of ln x looks like?
Yeah.
Yes. Can we think, I would like to think, even if, pretend like you don't already know that the graph, so it is true, the graph continues to go up. How do you know the graph continues to go up here? It has to do with this as a definition.
Just the area under the curve is increasing.
Yeah, right. This graph, when you say this graph is going up, really what you mean is this area continues to increase. And I hope you agree, it does. If this x goes out to the right, this area under the curve does continue to increase. It doesn't become 0 at some point. It just keeps on getting bigger and bigger, right? So the area from 1 to x, it is positive over here, and it continues to increase, although it increases kind of, I meant to write this in, it increases kind of slower and slower as it goes. That's because over here, this area increases slower and slower as the x goes off to the right. And what about if the x goes to the left of the 1? Well, for reasons like we said before, this area now begins to be counted as negative. So it becomes negative, and in fact, as you go closer and closer to the origin, this area becomes super duper increasingly negative because this area is becoming infinite here, all right? And so that means what I just said, super duper increasingly negative. I'm not afraid to sound foolish when I'm talking about math, all right? The reason it goes down super negative is because this area, if you measure it towards the origin here, is actually an infinite area. It's going up forever. And so this graph is going to infinity, but it's negative because it's negative area. All right? This is how you can get this basic picture from using that as the definition. Excellent. Great. What about these values over here? I had mentioned before, for instance, well, everybody knows the log of 1 is 0. What about the log of 2? Now that represents the area from 1 to 2 over here. That you can estimate that area by Simpson's rule or something, and it ends up being something like 0.6. I plugged this into my calculator before. 0.693, whatever, right? One thing to wonder is this curve here, does it have a horizontal asymptote that this approaches, or does this increase upwards forever? Anybody happen to know? I mean, the way I drew it, it's not really obvious on my picture. Does it actually level out at some point, or does it just continue to go up forever, but it's more slowly as it goes?
Go up forever.
It does go up forever. Yeah, there is no horizontal asymptote of the natural log. It does go up forever. And one way that you can see why that is I could do something like, everybody knows the log of 2. Well, not everybody knows, but this is, like I said, you could calculate this. It's something like 0.693 something. That means, for example, the log of 4, the natural log of 4, you could write this as the natural log of 2 to the power 2, which is, using that rule, 2 natural log of 2. So this is 2 times whatever that number is. It's like 1.3 something, right? It's 2 times the natural log of 2. You can do this on your calculator also. Or I could plug in log of 8. That would be 2 to the 3, which would be 3 times that original number. So these answers, they continue to go up forever. This 2 is something at like 0.69. This 3 is something at like 1.3, all right? And so on. The values increase slowly, but they do increase eventually up as high as you like, just very slowly. And what that means is this is one of our last favorite things to discuss, and something we're going to discuss in more detail later on. Check it out. The log of 2 equals 0.693, something like that. This is approximate, of course. And the log of 4 equals 1.3 something something. The natural log is a continuous function. What this means is I have one value that is less than 1 and another value that is greater than 1. This means there must at some point be a value which equals 1. All right? So there is some number I'll call it, a for now, where the natural log of a equals 1, right? That's because I have one value that's less than 1 and another value that's more than 1, and because it's a continuous function, the line has to at some point go through a value which equals 1. There's actually a name for that thing about the in-between. Anybody remember this? This is one of the big sort of theorems of basic calculus. This is by the, I'll give you a hint, value theorem. You heard of this? Yeah? The intermediate value theorem. Yeah, right. He said IVT. There are a few value theorems in calculus. There's also something called the mean value theorem. There's something called the extreme value theorem. This one is the intermediate value theorem. It says if a continuous function has one value somewhere and another value somewhere else, then there are points in between, that's why it's the intermediate value theorem, whose values equal the values in between. All right. So if one of these values is less than 1 and another is greater than 1, that means there has to be somewhere in between where the value equals 1. So that means as far as the graph looks like this. You have, here's 1, here's 2, here's 4. 2 is at like 0.6. 4 is at like 1.3, right? It means somewhere in between, and on my picture, let's say it's around here, I guess, where this equals 1. There actually is some number right there where ln of that number equals 1. And that number is called e. That's the definition of the number e. So this number is e. And that's the definition of the number e. This may be related to something that she said back at the beginning. You can define the number e in terms of some kind of area under the curve equals something or other. And that's basically those are the ingredients of what we're talking about here. All right, so this is the definition. I will write it again. E is the specific real number such that, if I want to be very clear about it, the integral from 1 up to e, 1 over t dt, equals 1. In other words, ln of e equals 1. Right? It's the specific number which has, which makes this area equal to 1. This is a much better definition of the number e. Better from an abstract point of view than the defining e to be the limit of 1 plus 1 over x to the power x, which is a lot harder to work with. All right. E, of course, is, anybody know the digits of e? I'm not sure why. People like to memorize the digits of pi, but nobody really memorizes many digits of e. I don't know many digits of either.
2.718.
Yeah, 718. Anybody know anymore? I wrote down on my paper 28, etc. All right. This is another irrational number, kind of like pi. This is an irrational number. For whatever reason, pi is something that ordinary people think pi is interesting, and mostly they have never heard of the number e. But for whatever you think is interesting about pi, the same things are true of the number e. There are Christopher Nolan movies called Pi, but he should make a sequel called E. It'd be awesome. All right. No, it wasn't Christopher
he
Nolan.
doesn't
It was
have-
Darren Aronofsky. Yeah, the other weirdo. All right, both talented filmmakers and weirdos. E is an irrational number. You want to hear a fun fact? This is a true fact that E and pi, of course, are both irrational. Everybody knows that. Anybody ever thought about this? E plus pi, is that irrational or rational? Irrational, remember, means that the decimal digits never repeat. You could think of it that way, or another way of saying that is that these numbers cannot be written as a fraction of whole numbers. Each of these have decimal digits which never repeat. What do you think about this number? Do you think it is irrational or rational? Anyone have an opinion? No.
Rational.
Rational? I would say, even if you have no opinion, this seems irrational to me. The question is, if you have these two numbers, their decimal digits never repeat, is it somehow possible if you added those numbers together? Like, I feel like the digits of pi are basically random, and so are the digits of e. If you say this is rational, that means by some magic, when you add them together, you actually get a repeating decimal, like they're all ones or something. But that's not true of pi and e. When you add them together, you basically just get some other bunch of nonsense. It's not anything. This, I will say, this is the fun fact that I'm here to tell you. It has not yet been proven that this is an irrational number. So this is, technically speaking, unknown if it's rational or not. Although, to this I say, those mathematicians better get to work on this. This is not, my own, I do some amount of my own mathematical research, but I don't do this kind of thing. This would be referred to as the type of mathematics called number theory. That is mathematics which is about numbers. Not all of math is about numbers, but the number theorists have been working for a long time on this one, and they got nothing. Everybody in their right mind would expect that this is also irrational, but it is, technically speaking, not known. Very strange. Strange but true. All right, that's all I need to say about that one. Can we talk a little bit about derivatives involving logs? And then we'll move on. I want to say a little about derivatives and integrals, and then that'll do us for today. We got about 20 minutes left. How about, derivatives and integrals involving logs? I would say ln of x. All right. First of all, there is the basic rule: the derivative of the natural log is 1 over x. All right. Everybody should know this rule. I think probably you already did. But if you didn't, that's it. It's not that complicated. The derivative of the natural log of x is 1 over x. Now, you often want to consider the derivative of a log with some other stuff inside of it, not just x, but some other stuff. If there's other stuff inside, what I mean by that is if you have something like ln of some other function on the inside like that, and I want the derivative, of course, then you have to use the chain rule. So I'm going to use the chain rule. The chain rule, of course, says when you take the derivative of something inside of another something, you do the derivative of the outer function first, keeping the inside the same, and then you multiply separately by the derivative of the inside. So when I do the derivative of the outer function, that's the ln. The derivative of ln is 1 over whatever. So derivative of the ln in this case gives me 1 over g of x. You should not modify the g of x in there. It's just 1 over the original inside. And then times, this is the chain rule, separately times the derivative of the inside, which is this. All right? So that's 1 over, that's the derivative of the outside, leaving the inside the same, and then times the derivative of the inside. That's how we do the chain rule. So this is often in textbooks written as a special formula. it says the derivative of ln g of x is, sometimes they like put the fraction together if you like. This you can, put in a box in a calculus textbook. To me, as far as like memorizing formulas, like I think I've said before, I'm not really all that big on memorizing formulas. I really just remember this one. And then when it comes to doing something like this, I remember how to do the chain rule. But this, if you like memorizing formulas, you could remember this one as a special formula by itself. All this is, though, is this one, including the chain rule as part of it. All right? I got a few simple derivatives for you all to try involving the natural log. Try these derivatives. These are probably, I hope, things that you already knew how to do before today, but just so that we're all on the same page here. Maybe I'll give you a few minutes to try these out. I'll walk around and see what you feel. In each case, all of these, actually, you can use something like the formula at the top there, or just remember the 1 over x thing with the chain rule.
I just didn't realize that was an option.
Everybody got this checklist, right? All right. Oh yeah. Suddenly, before you go into this.
That's fine.
It's a while.
Yeah.
Yeah, it does. It went for like 4 minutes. All right, let's talk about these because I have a few integrals that I want to talk about also. So the first one is very simple. If you just plug into the formula that you see at the top there, it is g prime of x over g of x. So the same thing on the bottom, x squared plus 5x minus 1, and then the derivative of the inside would be 2x plus 5. So that's just plugging into the formula at the top there. You could also have thought of this in terms of basically 1 over x, but using the chain rule, that would be 1 over x squared plus 5x minus 1, and then separately times the derivative of that, which is the same thing as this. All right, that was the easy one. How about this here? There are a few ways you could think this through. One way is to simplify. I think the easiest way is to simplify the log a little bit first. Well, regardless of what you do, you should do that first. Think of the square root as a 1/2 power. Now, you could take the derivative of this at this point, which involves using the chain rule twice, or you could use the rule about logs, which is this exponent can come down to the front. That's a little easier, so I'm going to do that. Let me get this guy out of here for now. I'm going to bring the exponent down to the front, so it's derivative of 1/2 ln 3x minus 5, like so. The 1/2 can just move all the way out of a derivative. It's a multiplication by a constant, does not affect the derivative. And then the rest of it, log of this gives me 1 over 3x minus 5 times the derivative of the inside, which is 3. So something like that that to me is the easier way to do it. And the other way would be to directly take the derivative at this point. It would give you something like, well, it's 1 over that, and then separately times 1/2 3x minus 5 to the negative 1/2, and then times 3. That's the chain rule twice. I prefer this way here. All right? Any questions about that one? And then the last one, I scrolled it down. This is actually easier than the other ones, but I put this in there just to make a point here. Negative x becomes 1 over negative x, and then the chain rule times negative 1, right? And this, of course, can simplify to just be 1 over x again. All right. So it turns out that the derivative of this one is not very interesting as a thing by itself, but it is interesting to point out. So, of course, everybody knows the derivative of natural log x equals 1 over x, but also, and apparently the derivative of natural log of negative x also is the same, 1 over x, all right? Log of x and log of negative x have the same derivative. What this means is when taking the derivative, this is a little weird, but when taking the derivative, the sign of the inside of a log doesn't matter, right? Log of x, natural log of x and natural log of negative x, their derivatives are the same. That sign is irrelevant. And so, for this reason, this formula is often written in this way. The derivative of the log of absolute value of x equals 1 over x. Why the absolute values in there? Well, this statement is true without the absolute values, then that's the same as this one. It's also true with a negative sign, though, and to sort of summarize those two things together, people write the formula like this, with the absolute values. It doesn't matter what the sign is in here. The derivative is always 1 over x. And so, writing this the other way around as an antiderivative, it would say this, antiderivative 1 over x dx equals natural log of absolute value of x plus c. Depending on where you're reading in, books which have a bunch of formulas of integrals, you will usually see it written in this way with the absolute value signs in there. And you may from time to time wonder, do I really need those absolute value signs? Or what is that even all about? It's all about this sort of weird fact about how changing the sign inside of a log in a derivative doesn't affect the answer. Do I really need the absolute value signs? The answer is technically yes, they should be there. Although I would say in almost all cases, if you are actually trying to use the natural log, you're not going to be plugging a negative number into it anyways, and so practically speaking, this usually doesn't really matter, but as a technical matter, you should put the absolute value signs in there. All right. All right, our remaining 10 minutes, I would like to discuss some using the log in U substitutions. So ln often appears, maybe I'll say unexpectedly, when doing the U substitutions. Here is a typical example. How about integral of 3x over 4 minus x squared? Now, we have a quotient inside of the integral. This is not something that you can easily do the integral of. The antiderivative of this is not, you absolutely cannot just do the integral on top and also do the integral on the bottom. This is not allowed. We can, though, do the U substitution. Would anyone like to suggest, what should I use for the U? There aren't that many choices. You have to choose a piece of that formula and call it U. What do you think?
4 minus x squared.
4 minus x squared. Yeah, if you've done this before, I mean, your choices are kind of, well, I could choose the top or I could choose the bottom. And it turns out that choosing the bottom is often a better idea. Choosing the top usually doesn't get you anywhere, but choosing the bottom is often helpful.
The way I did it is I made the bottom to -1, and then I put those in parentheses and made it U. Is that like?
Sure. Yeah, you could do that. So I will write this suggestion from before, but I'll say something about doing it that other way too. You would do the U and the DU this way. Now, what he said, you could also, and this is not a bad idea. Sometimes people have the opinion that just like putting stuff in a denominator at all is just confusing, and it's easier to think of it if you sort of bring the denominator up and make a -1 power. At this point, you should be using the same U, though. Maybe it's even a little clearer here why the denominator is more useful, because it's a thing inside of something else, and that's typically what you choose the U to be. So if you want to work it out this way, that's great. Anyway, I'm gonna stick with this approach on the left side. So now, du is -2x dx. I will, as usual, divide this constant onto the other side. -1/2 du equals x times dx. So when I write this, what I see is 3x over u dx. All right. And as usual, I'm going to try and simplify that and write everything in terms of u's and du's, not x's and dx's. And towards that end, I will take the 3 out of the integral, and then I have 1 over u, and then I took the 3 out here, and I like to split up this fraction. It says x over u, but I'm going to write it as 1 over u times x dx. And why I did that is because I see x dx, which is also what I see up here, is equal to -1/2 du. As usual, the U substitution, if lots of people like to write this in a different way, and that's totally fine with me, but this is how I'm going to write it. So I get 3 integral 1 over u, x dx is times -1/2 du. And then that -1/2 factor on the inside can come out of the integral, like so. And now the substitution is complete. Everything is now in terms of u's, no x's. And what is the integral 1 over u du? It is natural log of absolute value of u plus c. I'm always going to put the absolute values in there, and technically they should be there. Yeah?
So, I don't know this track. Wait. So you don't do the antiderivative, or do you?
I do. That was this step right here.
Oh, okay.
1 over u turns into ln absolute value u.
Okay.
That's the antiderivative. Yep. And one more step. Step that a few of you forgot to do on the quiz, tragically missed out on a point. Put the original variable back in. Instead of u, let's put the x's back in. So this is -3/2 ln absolute value. U is 4 minus x squared. plus c, like that. There you go. All right. This is what I meant when I said the ln often appears unexpectedly. Like, there's nothing in here about the log to begin with, and there's nothing in here about exponential functions or anything like that. So from a naive point of view, I would say, looking at this integral, I don't expect the answer to have anything to do with ln of anything. But actually, it does have to do with ln of anything. Where did the ln come from? I mean, well, technically it came from this right here. But I would say, if you have some kind of slightly more sophisticated view of what the ln is, the ln arises when you have a denominator in an integral. At least sometimes it does. Because the definition of ln is it's the integral of 1 over t, something or other. Which is why it's maybe not so surprising, starting with this, that you do end up with the ln at some point. All right. Let's just try one more example. We got a few more minutes. How about, this one is maybe a little simpler than the one we just did, although it's kind of cute. Tanks. The integral of tangent of x. Everybody knows the integral of sine and the integral of cosine. I said before, I don't necessarily expect you to have the integral of tangent memorized. Because, I mean, one reason is you can actually work this out using only sines and cosines. Would anyone like to give a suggestion towards that end? Like this, you can actually rewrite. I hope you remember one little thing about tangent.
Isn't it sine x over cosine x?
Yeah, right. This, I hope everybody remembers. Tangent is the same as sine over cosine. That's really the only sort of special fact that I will expect you to remember about tangent. And essentially, every time you see tangent in this class, you should immediately rewrite as sine over cosine, and cotangent as cosine over sine. All right? Okay, and now we're going to do, from here, the u substitution. Would anyone like to suggest what to choose for the u? Cosine, yeah. Generally speaking, if you're using a fraction with the substitution, you should choose the denominator, the whole denominator, usually. So u is cosine x. The du then? What do you say? Negative sine of x. Yeah, I hope you can somehow keep straight when to introduce the minus sign. The derivative of cosine is negative sine dx, of course. And if I move the minus sign to the other side, it would say negative du equals sine x dx. So when I go back to plug in here, it's sine x over u dx. Sort of splitting apart this fraction, 1 over u, and then the rest of it is sine x dx, right? And I wrote it that way because sine x dx appears in my, that's equal to negative du. 1 over u times negative du. We can factor the minus sign out. 1 over u du. All right? So this is the substitution. As far as substitutions goes, it's not all that weird. And then we can finish it off. 1 over u, the integral of that is natural log u. So it's minus natural log absolute value u plus c. And then finally, replacing the u, minus ln absolute value cosine of x plus c. This is the derivative. Maybe or the integral of tan. I'll write that again. Just to summarize. Here's an example where the absolute values really kind of do matter, just because you're never supposed to plug a negative number inside of a natural log. But of course, cosine is often negative, right? It goes up and down. So if you don't have these absolute values, this is going to be undefined in a lot of places when actually it should be defined. So put the absolute values. All right, that's it. Let me know if you have homework questions. We can talk tomorrow, of course. Let's do tomorrow. Have a good one.